Suppose you're in a machine learning engineering interview and the interviewer asks you this: our new model just hit 95% on MMLU, beating GPT-4. The marketing team is drafting a press release. As the engineering lead, what's the first thing you check for that could invalidate this result? Pause the video and think about how you would answer. When you're ready, press play and we will test your first move. Almost everyone starts in the same place, and they are right to, because if the test questions were in the training data, the score means nothing. So we check. Here is one of MMLU's 14,079 questions from the anatomy section, and we take its exact text along with every other items and search our training corpus. 0 hits. The corpus is clean. That would settle it, except that someone checked MMLU's answer key and counted the mistakes in it, and there are enough of them that this test cannot prove a score as high as 95. Both of those cannot be true, and the scan did not fail because the question it answered was not the right one yet. There are 3 reasons this number might not mean anything. Nobody could have measured it, we measured it wrong, or we measured it right and did not earn it. A good answer tells them apart and says which one to check first. So we start where the checking is free. The free check is the test itself. MMLU is 14,079 multiple choice questions written by people, and researchers re-annotated 5,700 of them by hand across all 57 subjects. 6.49% of the questions contain errors. In Virology, 57% of the ones they examined. Sit with what that does to a score. If an item's answer key is wrong, a model that reasons its way to the genuinely correct answer is marked wrong, and to be scored correct there, you have to reproduce the key's particular mistake. Reasoning cannot do that. Having seen the key can. So past a certain accuracy, a higher score stops being evidence of a better model and starts being evidence of a mechanism. That costs nothing, and it points to the next question. Where did the extra points come from? Pull the score subject by subject, one query against a file we already have. If the extra points sit in the subjects with the worst answer keys, we have learned a lot, and if they sit in the clean ones, the number may be more real than it looked. Which leaves 2 explanations. We measured it wrong, or the model had seen the answers, and the first one is cheaper to test. 95% on MMLU names a dataset. It does not name how the model was asked, or how its answer was read. And those are the instrument. Take our anatomy question. One scoring rule compares the model's probability for each of the 4 letters. Another compares the 4 full answers. A third lets the model write its own answer and matches that to an option. 3 different questions. Watch them disagree. Only the rule changed, and at most one of the 3 is scoring the question correctly. Hugging Face ran the same LLaMA weights through 3 implementations. The 65 billion parameter model scores 49% under one and 64% under another. 15 points from the harness alone. GPT-4 scores 86.4, so our claim beats it by less than 9. So rerun under the same implementation that produced the GPT-4 number and diff the configuration, because if the score drops, we are finished and need no corpus audit. Then confirm the few shot examples came from the dev split and not the test split, since a harness that shows test questions to the model never copies them into the corpus. Suppose it reproduces. The number is real, and the only question left is whether it was earned. Here, the answer that sounds strong is to stop matching strings and run a semantic audit, embedding everything and looking for near duplicates by cosine similarity. It is a better answer, but not a sufficient one, and we can watch it fail. Take our anatomy question and write it 3 other ways. A paraphrase, the same question in another language. A forum post working through the answer. The exact match scan finds none of them. The embedding search finds the paraphrase immediately. On the translated one, with a standard sentence encoder, it does not fire. Here's what that gap is worth. Yang and colleagues rephrased benchmark test sets and trained on the rephrased versions. A 13 billion parameter LLaMA 2 went from 54.8% on MMLU to 89.9. GPT-4 scores 86.4. Above GPT-4 with no capability gain at all, and n-gram decontamination sees nothing. That is the press release we are about to send, and somebody produced that result on purpose. This does not have to be on purpose. Nobody built StarCoder data to cheat, and 26 of the 164 problems in the human eval coding benchmark are sitting in it rephrased. CodeAlpaca has 21 of them. So we go looking for it. The obvious move is to index the corpus and search it, which is the most expensive check on the list, and not where to start. There is a cheaper test that checks what marketing is actually claiming. Do not ask whether the test questions are in the training data. Ask whether the model scores as well on questions that cannot be in there. Pay people to write fresh questions in the same style and difficulty after the model was trained, and score the model on those. Scale AI did this for grade school arithmetic, writing GSM1K to match the older GSM8K and measuring the gap. Accuracy dropped by up to 8%, and several model families dropped at almost every model size. Many of the best models barely moved at all. This test can come back clean. But if the gap is large, there is no press release. Only then is a corpus audit worth its cost, and you start with the cheapest check and pay for the next one only if it comes back clean. The one that works ends with a language model judging each pair, and the embedding search only picks which pairs to look at. That is enough to answer out loud. Before I check anything, I would separate 3 failures because each one needs different evidence and costs a very different amount. First, whether MMLU can even show a score this high, because somebody has counted the errors in its answer key, so above some level, the extra points come from repeating those errors rather than from knowing more, and that check costs nothing. Second, whether our harness produced the number honestly, which takes one rerun using exactly the setup, the baseline used. Only if the number survives both would I spend anything on looking for contamination, and I would start with fresh questions rather than a corpus scan, because it is cheaper and it measures what we actually want to claim. 4 sentences, 3 branches, and no method named before the reason to use it. And the order is forced. Each check is the cheapest one that could still prove the number wrong. One condition changes. The model is not ours. It is a vendor's or an openly released model whose training data was never published. Same number, same benchmark. Where does that sit on the tree? The answer key check works no matter who owns the model. Still free, still first. The harness rerun works too, as long as we can run the model ourselves, and it is now the strongest check we own. What we lose is the bottom of the other branch. No corpus means nothing to search, nothing to index, and nothing to compare embeddings against. The audit that sounded like the strongest answer is the first thing we lose. The fresh questions test is unaffected because it never needed the training data, only new questions to ask. And one more check becomes possible if the vendor gives us token probabilities. A model that never saw the benchmark file should rate every order of its questions as equally likely, so rating the published order higher means it saw the file. One rule here is worth taking away. Prefer the checks whose evidence you will still have when the conditions change, because a check that needs access somebody else controls is the one you lose exactly when you need it most.